Okay, for now I want to conclude this series of podcasts with the concept of atmospheric rivers. They are called atmospheric rivers because we are looking specifically at condensed water. This nice infographic from NOAA is helpful. So here an atmospheric river is a flowing column of condensed water vapor in the atmosphere responsible for producing significant levels of rain and snow. Especially in the western United States. Okay, when ARs or atmospheric rivers move inland and sweep over the mountains, the water vapor rises and cools to create heavy precipitation. Though many ARs are weak systems that simply provide beneficial rain or snow, some of the larger, more powerful ARs can create extreme rainfall and floods capable of disrupting travel and inducing mudslides and causing catastrophic damage to life and property. Okay, so we can look at this website. This is showing a strong AR transports an amount of water vapor roughly equivalent to 7.5 to 15 times the average flow of water at the mouth of the Mississippi River, one of the big rivers in the US, and this is giving a relative size. ARs are a primary feature in the entire global water cycle and are tied closely to both water supply and flood risks, particularly in the United States. I'll just read it even though it's very specific to the United States. So here, on average, about 30 to 50% of the annual precipitation on the west coast occurs in just a few atmospheric river events and contributes to the water supply and flooding risks. ARs are approximately 250 to 375 miles wide on average on the west coast of the US, coming all the way from Hawaii on to California and other regions of the west coast. ARs move with the weather and are present somewhere on the earth at any given time. So there are always ARs running around on earth in the atmosphere. Scientists' improved understanding of ARs has come from roughly a decade of scientific studies that use observations from satellites, radar, and aircraft, as well as the latest numerical weather models. More studies are underway, including a 2015 scientific mission that added data from measurements aboard a NOAA ship on the North Pacific, Northwest Pacific off of California. So, dynamically speaking, if you can identify an atmospheric river or predict it miles away, then obviously you got a chance of predicting heavy precipitation, right? This is the point. So just to move into the monsoon region, by the way, there is a very nice image from the UCSD field study mentioned here that combines satellite data and shows a beautiful atmospheric river flowing from Hawaii all the way over to California that caused some heavy rain and mountain snow. Okay, topography is mentioned here as a key feature to extract rainfall out of atmospheric rivers, which obviously on the Indian west coast you have Western Ghats and you have the Himalayas to the northeast to North Indian Ocean. In terms of the definition, you are basically looking at integrated water vapor transport, which goes from some pressure level, typically let's say at the surface or the boundary layer, to some level in the atmosphere depending on the vertical structure, which we will look at in a minute. So you take specific humidity multiplied by the wind speeds that are carrying, so it can be meridional and zonal. So you can clearly see here the atmospheric river has a zonal component and a meridional component, and you integrate in the pressure level divided by G to get you vapor transport in grams per second integrated. And it is also to be related to the precipitable water, which is just the same integral but just of the specific humidity in a atmospheric column. So that's a local measure of how much water vapor is loaded. And you can see here the associated moisture river detected on 25th July 2010. And to highlight the region of the river, it is taking 85th percentile IVT threshold as a criterion. So you can see that water vapor is coming all the way across from south of the equator, from the marine ITCZ region that exists in July, comes up with the south easterly winds, crosses the equator, and becomes southwesterly, bringing this moisture onto India. And there is of course the back component of that coming from the Bay of Bengal. The structure of the low-level jet or the fin-later jet always tends to be very complicated. Flow is going around the peninsular India and Sri Lanka onto Bay of Bengal and curving back, and there is a lot of direct transport with the jet. And you can see the orographic impact and the loading of the precipitable water here. That is a seasonal feature depending on where the monsoon trough is. So here, this paper by Thara Prabhakar and her group from the Indian Institute of Tropical Meteorology from 2019 also looks at rainfall amounts and the it's a scatter plot showing the relationship between the integrated vapor transport strength maximum on detected moisture river over the Arabian Sea and corresponding west coast daily rainfall over the 30-year period. So it's taking 30-year periods, it's taking maximum integrated vapor transports for each month during each month, and identifying rainfall amounts associated with those maximum vapor transports. So for June, which gets about 20% of the seasonal rainfall, but the Western Ghats get almost 2 meters to 3 meters of rainfall. So obviously the strong atmospheric river we see here has a role to play it, and it has a seasonality because the strength of the jet itself changes and its direction also changes on intraseasonal timescales and also on interannual timescales. This combines all of those together, so the El Nino effects on the dynamics and the atmospheric river and all those things have been merged into this scatter plot. But nonetheless, you see that as the maximum IVT in kilograms per meter per second increases, remember it's been averaged in the vertical, so the unit is kilograms per meter per second. So you take the range here from 400 kilograms per meter per second to 1400, and you expect that as the IVT increases, the strength of the atmospheric river increases and the amount of rainfall increases as well. So here the slope is much smaller than the slopes in July and August, as well as the minimum IVT maximum is smaller in June as the monsoon is building up, versus you can see the minimum numbers here are different for each month. So much more clustering here in this range. So July and August are obviously the peak rainfall seasons, which means the strength of the fin-later jet and the atmospheric river changes as well. So you can see the extremes here are 400 meter per millimeters, whereas here it's higher, up to 500. Here also it's a bit higher. Okay, so there is a seasonality to the atmospheric river. For the Indian monsoon, the which is a much smaller domain with a warm ocean in general, even though the fin later jet cools the waters in the Arabian Sea, which is a predominantly evaporative basin during the monsoon season, and there is strong coastal upwelling created by the alongshore winds as well. So a lot of moisture comes from south of the equator, and then a lot is added here. But the Bay of Bengal remains a warm basin throughout the season, and also has a lot of rain, so a lot of the atmospheric water vapor is extracted out here, but nonetheless there is back circulation creating the cyclonic gyre, and of course you have the low pressure systems and monsoon depressions, which also bring in water vapor, which also can add to the atmospheric river. So the mean dynamics and the atmospheric river obviously are very closely connected, and that is all going into these rainfall, and you can see the relation is only 0.5 correlation between rainfall and the IVT here is 0.59, 0.56, which are obviously statistically significant, but it jumps, the scatter decreases, the relay correlation jumps to 0.71 in August. So this is potentially related to the distribution of extremes during the season as well. India is getting more large-scale extreme events during August and September. September is not shown here, and the interannual variability also tends to be much higher during September, for example, compared to June and July and even August. Okay, all those things are related to each other. Looking at one specific example from Munir Nayak and his group's paper that looked at the incredibly heavy flood that occurred over Kerala, quite widespread, as you can see here, going over hundreds of kilometers, and the rain rates are also quite large, going from around 50 millimeters to more than 400 millimeters on certain days here and on local spots. This was a return period of almost 100 years. I think such a large flood had occurred back in the 1920s, and then it occurred in 2018. This is from 2018. Heavy floods also occurred in 2019 and 2020, so one has to see whether the frequency of the extremes here is changing very rapidly as well. But nonetheless, you expect that such heavy rain events are going to require a lot of moisture, which is obviously not available on land, so atmospheric river there plays a critical role. Orography is definitely a big part of it, as we saw in the case of California, where atmospheric river is bringing in all this water, and orography is going to squeeze out the rainfall out of it due to rising air and expanding cooling air and dumping rainfall. But also the question remains whether the demand for moisture comes from instabilities that are occurring on land and pulling the low-level jet and demanding moisture, or whether the moisture is somehow trucked in on its own because of the dynamics and ocean evaporation, and then creating orographic rain. This is a critical question in terms of the Indian monsoon, which is very unique with its peninsular continent coming down so deep into the tropics, and the fin later jet, which is waxing and waning at seasonal timescales as well as on intra-seasonal timescales, because the timescale of these advection are several days and maybe even longer than a couple of weeks. So even if you could predict the atmospheric river, you have to predict where it's going to go and how much rain is going to be produced based on other parameters, maybe potentially the moisture demand up here or orographic rain along the coast. right? So these are complicated questions, but at least predictability of atmospheric rivers is going to add to those kinds of details and allow predictions to be more skillful. The integrated vapor transport in this case was defined in this way as a scalar of the zonal squared plus meridional squared and its square root. This study also shows the climatological atmospheric river. So this is showing for 13th August 2018 here, and for the same day as a climatology of 30 years or so. So you can see that climatologically on that day, this is what you expect in terms of the water vapor transported in kilograms per meter per second. But on that particular day, that you can see that the water vapor transport is much higher, going from order 600 or so kilograms per meter per second to almost 1200 kilograms per meter per second, so almost doubled. And the maximum is over here, which tells you that the contribution is coming from different places, and Bay of Bengal is always a warm ocean and has heavy convection, so it is possible that the convection over here is demanding moisture and pulling the Findlater jet and the water vapor transport here, which is then dumping rainfall here because of orographic effects, right? So these are the orographic rainfalls. So those kind of questions are important. This study also did back trajectory transport. You can look at the details. I just want to introduce the concept. And this model does several layers. So it's a pressure layer, but they are have a thickness when you average over time. So you can see those as 500 meters, 750 meter, and so AGL is the average level in the model, and the black line is the mixed boundary layer. So you can see that most of the contribution is looking at the colors and the scales of water vapor transport in kilogram per meter per second. You can see the range here. A small amount is also coming off from the extratropics and mid latitudes. So when the demand is high, maybe the moisture is pulled in from wherever possible. So way down towards the Southern Ocean almost, and there is also a time scale given to this in the paper, which I'm not going to show, but obviously a lot of it will get picked up in the tropical, subtropical regions, but over time moisture is being pulled over here as well. So the time scale matters, and the key question always is whether these are coming up and then creating extremes, or whether some kind of instabilities are demanding these kind of moisture loads. But considering the time scale of how long it takes for the water vapor to come up here, it's possible that it's a combination of things. How much water vapor and water is available in the atmospheric rivers, and what kind of instability occurs when they are available. So the combination may be what produces these 100-year type of events. And then the question is whether the global warming is loading the dice and creating more of these heavy events with return periods of 30, 50, 100 years, whether they are becoming more frequent 5, 10, 15 years and so on. So this is something that has to be understood. But the atmospheric river phenomenon obviously is very important for the Indian region as well, and their contribution to subseasonal versus higher frequency extremes obviously has to be understood better as well. And there is some early work that shows that even the monsoon onset is affected by the atmospheric river that is building up before the monsoon, and then the monsoon trough moves in from northwestward from the almost as far as northwestern tropical Pacific, and when the confluence of the Findlater jet that builds up and the trough that comes in, so the dynamic and thermodynamic components combine to kick up the rain over Kerala as an onset, and then it moves northward, and then the atmospheric river begins to interact with the rainfall over land and the dynamics of the Findlater jet. Okay, so that's just a brief introduction. Again, you can catch up by reading excellent papers from California groups which have looked at this a lot, because for them it's a very critical feature that is related to the distribution of rainfall, including extreme rainfall.